So in today's video, I'm going to talk about using finite differences to solve one-dimensional partial differential equations. And the basic idea is we're going to take a partial differential equation and then using the finite differences approximation, convert that partial differential equation into n coupled ordinary differential equations. And the concept is very much similar to when we did boundary value problems. Really the only difference is we're going to use ODE int rather than the root command. So let's start out with our first boundary value problem where we have dc dt is equal to some diffusion coefficient times d squared c dx squared. And we're going to have two boundary conditions. The left boundary at x equals -1, we're going to fix the solution at 1. And the right boundary condition at x equals 1, we're going to set the solution equal to 2. And then our initial condition is that when time is equal to 0, c is equal to 0 everywhere in the interior except at the boundaries where it's 1 and 2. So basically, the idea is as before, we're going to set our grid. So let's just start with n because that's nice and simple. We're going to define our domain, which is going to be np linspace. And because we're going from -1 to 1, we're going to go from -1 to 1, right? Because our left boundary is at -1, our right boundary is at 1. And then we're going to have n points. And then we're going to set delta is equal to x of 1 minus x of 0. So the distance between the node points. And we could just use the first two x's to determine that. And let's just grab a diffusion coefficient and let's just pick it equal to 1/2. So the first thing we're going to do is define our function. So f, and it's going to have to be a function of c and t because we're using the ODE integrator. And so the first thing is I'm going to do is just initialize dc dt, right? I'm going to set that to be a vector or an array equal to the size of c, and I'm just going to zero it out. And then I'm going to return dc dt. So the basic idea here is for I, we're going to do the interior point first, from I to range to n-1. So these are our interior node points. We're going to write an equation almost identical to what we did with our boundary value problems. We're going to say dc dt of I, and then we're going to apply our finite difference approximation. So c of I plus 1 minus 2 times c of I, and then c of I minus 1, and then we're going to do delta divided by delta. And so that's going to give us our solution of c in the interior. And so the only other thing we have to do is our boundary conditions. And so in our boundary conditions, our left boundary condition is 1 and our right boundary condition is 2. Now the key thing is that if you look at this function, you see that c of t at x equals -1 is a constant value. So it's just equal to 1. So as time changes, this value doesn't change at all. So if I was to take the derivative of this, basically the derivative at x equals -1 is equal to 0 because it's just a constant. So even though I don't have to write this equation, I will because it's actually kind of encapsulated up here. We're initializing the derivative is equal to 0, but I'll just write it out here to make it clear. So our left boundary condition is we're saying dc dt at -1 or at 0 is equal to 0, right? Because it's just not changing as a function of time. And what we're going to do is we're going to actually incorporate these values into our initial conditions. And likewise, dc dt, our right boundary condition, dc dt at the last point, -1, or equivalently at n-1, is also going to be equal to 0. And so that's going to be what we're going to solve. Next thing we're going to do is define our initial condition. So define our initial condition. We're going to set c naught is, because it's zeros, we're going to just set np equals zeros of n. And the only thing we're going to have to do is just adjust this for our boundary condition. So we know the leftmost point is equal to 1. So c naught at the leftmost point is equal to 1, and that's our left boundary condition. And then c naught at n-1 is equal to 2, and that's our right boundary condition. So the next thing we have to do is just determine our times. And let's just take linspace, and let's just integrate this from 0 to 2. And let's pick 5 points. And then I just solve it. So I do ODE int. And then I'm going to do my function, my initial condition, and my time span. And let's make sure it runs. And again, C, what's going to be returned to us is an array. And the rows of the array are going to be the different times of the solution. So there's going to be 5 rows. And then the columns are going to represent the solutions for the different values it sees at the finite difference node point. So there's going to be 10 columns in this. So it's going to be a 5 by 10 matrix. So the easiest way to plot this up is just plot up the individual curves. And so I like using enumerate for this. So enumerate is going to give me the index and the time, and enumerate t-span, right? So it's going to go through the different t's and also the index value of that t. And what I can do here is just do plt plot x comma c, and I want to go row by row to plot the solution, right? Because we're doing different times. I'll do line width is equal to 3, and then let's put a label here, and we can say t is equal to percentage point 2f, and then percentage t. And this is going to just show us our legend. We can do plt legend, and then plt show. And I run it, and now you see the solution. And so if you look at the blue line, this is our initial condition. We see that it's 0 in the interior, and at the left boundary it's 1, and the right boundary it's 2. So it satisfies our boundary conditions. And if we look at all the other times, we also see it satisfies the left boundary condition, the right boundary condition. The reason why is we set these initial conditions at the boundaries, and then as we integrate it at those points, we just set those derivatives equal to 0, which means they're constant. They're not changing as a function of time. And then the fusion is through this equation. It's a little bit choppy because we only use 10 points. And so if we want to get a cleaner solution, we can do 100 points. And now we start seeing a cleaner solution where it's 1 at the boundaries, 2 at the other boundary, 0 in the interior, and you start seeing the solution evolve as a function of time. If you want to see more curves, we can pick 10 time points between 0 and 2, and then we kind of see the evolution of the curve, and then we have our legend over here. I'm going to hide the legend for now, just because it's a little bit messy. In the sample code I put on Compass, I actually show you how to stick the legend outside the plot, so it's not kind of overlapping the plot. So that would be one change in the solution. So the next thing is, imagine we wanted a reaction. So maybe you want to do c of t comma x squared, right? So now we have, so initially we had nothing here on the, we had no extra term here. And technically we could have solved this analytically using kind of the Fourier transform or Fourier series expansions. But once we add this nonlinear term here, basically there's really no analytic solution to the equation. And so numeric solutions are our only alternative, or at least I'm not aware of an analytic solution. There might be one that exists, I just don't know what it is. But just as before in boundary value, the only thing we're going to change is if we look at this, this is our dc dt, here's our dc dt. This thing determines our diffusion operator. So this is the diffusion part. And so if I want to add a reaction, all I'm going to do is just add a reaction. So I'm going to just do ci squared. Now, one of the things you're going to do, everything else changes. The boundary conditions haven't changed, so everything else is unchanged. What you're often going to see as I run this, you're going to get probably an error. Actually, it ran here. And what you see is the left boundary condition is 1, right boundary condition is 2. And it's a little bit more droopy here because we have this depletion term. Mathematically or physically, this would represent a second order reaction. So this would be diffusion where we have fixed concentrations on the left and right boundary. The molecules can diffuse in the interior, but then they can also, two of those molecules can react in a second order reaction and kind of deplete away. Sometimes if you look at longer times, if I go to 20, I run this, you get this kind of complaint that says excess of work done on calls. Basically, it's having numerical problems, and all you have to do is just tell it to do more work. And there's a simple option, which is mx step. I find just putting it as 1,000, basically telling to iterate at least 1,000 times will give you the solution. So now I run, it actually converges to the solution pretty fast. It basically jumps to steady state. Maybe if I put 100 points in here, you'll see you'll see kind of the evolution of the profile going forward. So that would be kind of the solution of a fixed boundary condition with a reaction term right here. If I want to change the initial condition, maybe I want to make it 2 up here, right? So now I have 2 for the initial condition. All I'm going to do is rather than C naught is equal to zeros, I'm going to set it as equal to C times 2 times 1s. So I'm going to set it equal to 2 everywhere. And then my boundary conditions are still the same, right? I'm going to fix the left one at 1, the right one at 2. And now when I run it, you see the initial condition is at 2, right boundary is at 2, left boundary it's 1, and then gradually you're going to see the evolution of profile, and eventually it's going to converge effectively to the same steady state as you had before. The initial condition will go away, because this is at least a stable system when it'll converge to one single steady state regardless of the initial condition. So that's kind of the overview of finite differences. It's not a lot of code, right? Really, this is the amount of code that we're doing to solve a fairly complicated equation, one that you couldn't actually solve really analytically. And that's the beauty of doing computation, right? And literally in a video in 5 or 10 minutes, I can solve something that might take, 10 pages of math to solve analytically. All right. So what happens if we want to do a no flux boundary condition, right? So at the right-hand side, we're going to have a no flux boundary condition. So let me grab the same code. So I'm going to come up here and I'm going to grab the 100 points because all I'm really going to do is change one line here. So let me copy this code. So the first thing is I'm going to get rid of this reaction term. So I'll get rid of that, right? So again, I have my dc dt is equal to the diffusion part, which is this part of the equation. My left boundary condition is unchanged. It's still equal to 1. But what's going to change is my right boundary condition. And the trick here, and in kind of the notebook I posted on Compass, I derived this for you. But here, what we're going to say is d c of n minus 2 minus c of n minus 1 divided by delta delta. And that's all we have to do to put in that right no flux boundary condition. And since we have a no flux boundary condition, we can get rid of this right boundary condition. So I'm going to comment it out. We only need this one because at the right-hand side, while the derivative is equal to 0, the value, in this case, it's going to be equal to 0. So it's no longer equal to 2. It's equal to 0 at the right-hand side because we're no longer fixing it. Everything else is the same. I'm going to just go from 0 to 2, and I'm going to pick 5 data points, and I run it. And what you see, whoop, I'm going to fix this initial condition. I forgot it. I meant to be zeros here because the initial condition is 0. And I have my 0. So initially I have right 1 and then 0 everywhere else. And then you start seeing the concentration profile evolve as a function of time. And you see at the right side, the boundary, the derivative is equal to 0. So the curve has a flat profile. If I wanted to look a little bit more in time, let's go to 5 seconds, maybe do 10 points. You're going to see, eventually it's going to converge all the way up till it gets to 1. So let me take a little bit more. Let's do 10 seconds. And then eventually it's almost flat at the top as you kind of converge to steady state. And if you want the legend, you can put in the legend to show the time values. But let's hide the legend there because it's a little bit messy. And so that would be a no flux boundary condition at the right-hand side. And all you're doing is this little bit of code. So now maybe I want to change this. So maybe I want to go back to my initial point where I had a fixed boundary condition at the right-hand side, right? And so that would be the right-hand side is equal to 2. And now I want a no flux boundary condition at the left-hand side. So let me just fix this, quickly typeset this. So I got partial here, and then I got partial of x. And whoop, we got a typo. Partial of x, where's my, I got that stray parenthesis there. And so now if I solve the same equation with a no flux boundary condition at the left and a fixed boundary condition at the right, what I'm going to do is get rid of this code, right? Because it's fixed at the right-hand side, so it's 0. And I'm going to uncomment this initial condition, but I'm going to comment the left one because we have a no flux boundary condition there. And basically we're going to write the same equation, just re-index. So I'm going to have c of 1 minus c of 0, all divided by delta, And now I run it, and you're going to see the right at 2, and the left has no flux boundary conditions everywhere. So that's relatively straightforward. Now, if I want to add a reaction, so just as before, I want to do c of, t comma x squared. So I have c of t comma x squared. What I'm going to do is before, I'm just going to do minus c of I squared here. But because we have this diffusion boundary condition, this is not exactly equal to the derivative equal to 0. We actually take this equation, apply this no flux boundary condition, the result is this. I showed the derivative derivation in the notebook. But here we would do minus c of 0 squared. So we also have to put the reaction term over here. whether you include this or not, it's not going to actually have a perceptible difference on the code since it's only 1 point out of 100, but technically this is the correct way to do it. And now I run it, and I have kind of the solution. So it's 1 at the right-hand side, 0 initially, and then because we have the reaction term, it's actually not going to converge to 2. We're always going to have the derivative, but we also have that no flux, our 0 derivative at this side. Last thing I'll do is if we have derivative boundary conditions at both sides. So I do 0, I do frac, let's do partial here, and then partial of x. And to make this a reasonable solution, so if it's 0 everywhere, it's going to be 0. So let's make the initial condition 2. So we're going to solve this equation. So the first thing we're going to do is adjust the boundary condition. So we're just going to come back here and do d. And just as the same formula I gave you, it's going to be c of n minus 2, all divided by minus c of n minus 1, divided by delta, divided by delta. And again, the math is in the notebook I posted. And for that node point, because this point, this 0, matches that 0, and this n minus 1 matches that n minus 1, and I got to put a 2 here. And then I'm just going to adjust the initial condition. So now it's 1s, and then I'm going to do 2 times here. And then since I don't have a fixed boundary condition, basically it's going to be 2 everywhere. And when I run this, basically there's no diffusion. You see the solution's initially 2, and then it's going to go 1 all the way down here because it's basically homogeneous everywhere, so there's no diffusion. So let's make it a little bit of interesting. Let's do 1 minus 0.1 x squared. So this is going to be our initial condition. Let's clean that up. Let's make a little bit better initial condition. So we have a little bit of a loop. So our initial condition is going to be 1 minus 0.2 x squared. If I want to write this, all I'm going to do is just type c of naught is 1 minus np exponential of minus x squared. And then I'm going to put the 0.2 here, there. And because the x is already defined my node points, I'm just going to put this equation here. I'm basically just typing in this equation for the initial condition. I have no flux on both the left and right, so I don't have to adjust the endpoints. And now I run it. And initially, it's kind of flat, and then eventually it's going to diffuse down and kind of flatten out. Probably if I do shorter times, it'll look a little bit better. And you kind of see it's initially curved and then initially flattens out. Problems with like no flux boundary conditions at both the right and the left is that because it's kind of insulated, everything is kind of homogeneous in the system, so we don't see the curves as nice. But the key thing is all we're doing is just typing in the function for the initial condition. And then here's the formula for the right no flux boundary condition. And here's the formula for the left no flux boundary condition adjusted with the 2 reaction rates at the ends. If we had no flux, if we had fixed boundary conditions, these derivatives would be equal to 0. And then we would adjust the boundary conditions. So maybe if we want to put in a fixed boundary condition again at 0 here, and then I could come back and make that adjustment point here at c of 1. And now if I run it, you see it's kind of ugly at the initial condition, and then you see the curves start evolving from there. So that's kind of an overview of finite differences. If you have questions, please post them to Piazza or put them in the comment section. But basically, you can use this template to solve the first 2 problems in your homework set. With that, I will say thank you and goodbye.